Hello, my name is Joachim, and in this video I will explain you the work of my master thesis, for which I was studying the theoretical description of so-called strongly interacting dark matter. In case you never heard about dark matter, I must tell you that the visible matter of everyday life makes up only 5% of the energy in the whole universe. The rest is so-called dark energy and dark matter. Unfortunately, we do not really know what this stuff is. But knowing that all visible matter is composed of so-called elementary particles, it is a fair assumption that also dark matter might be some sort of new particles, which seemingly do not interact with the particles of the standard model. However, just like visible matter, these dark particles might in principle interact with themselves. Some evidence that they actually do comes from observation of dwarf galaxies. One can, for example, measure the velocity of the stars in the galaxy as a function of their distance from the center. While the observations cannot be explained without dark matter, non-interacting dark matter fails to reproduce the profile at the center of the galaxy. Self-interacting dark matter seems to provide a better explanation for the data. The estimated value of this self-interaction is rather large. One natural explanation for these values could be that the dark particles have a certain spatial extent, since larger particles are more likely to scatter off each other. Such large particles typically reveal an internal structure, being built from smaller elementary particles. A dark matter model inspired by this idea consists of massive elementary particles, called dark quarks, which interact with each other by exchanging massless particles, called dark gluons. This interaction mechanism is often called quantum chromodynamics. At low energy, the force between two quarks is so strong in short range that they will only appear in pairs, forming a larger composite particle. However, not only one, but a whole zoo of such particles emerges, and these theories are rich and complex in structure. In fact, they are a bit too complex. Even calculating only the masses of the composite particles is quite a task, and calculations on paper quickly fail. There are numerical methods available, but they are expensive in computational time and resources. Thus, one better knows exactly what quantities to calculate, and hence, in order to start, we need yet another approach. Realizing that in most situations dark matter can be considered as cold or non-relativistic, it is enough to consider only the lightest states in the theory and how they scatter at low energies. A theory describing the interactions of a selected subset of particles, neglecting the others and their internal structure, is called a low-energy effective theory. The interesting aspect is that this theory is fixed almost completely by the symmetries of the underlying quarks. To better understand what I mean by that, consider for example that all quarks are of equal mass. Since now we cannot distinguish them anymore, we can exchange them without changing the physics. This is called a symmetry. Knowing the composition of the bound states, we can also learn how they transform under such a symmetry. And in fact, these symmetries are then so restricting that we can learn a lot about the system without doing any expensive calculations. In order to demonstrate what you can do with this, let us consider two scattering processes. First, two particles scattering off each other. This process determines the rotational velocity profile from the beginning. Second, three particles scattering into two. This process reduces the number of dark particles, and because E equals mc squared, it heats up the dark matter. From symmetries alone, we can now calculate the rate of these processes as an easy function of the same two parameters, which can be deduced by a computer simulation, and we now know what to look for and how this connects to, for example, astrophysical observations. There are many more questions that can be addressed by the symmetry-based approach, and for the model I investigated, some of them I answered in my thesis, hoping to contribute to a better understanding of strongly interacting dark matter.